All right, so we're going to start in here on chapter 2, and we're going to take we've got a kind of a short lesson with this one, but it's going to create some basic and fundamental ideas that are really concepts that are central to understanding calculus, and particularly understanding integrals inside of calculus. What we're going to do is we're going to start out with looking at the idea of the integral as an area under the curve, and then we're going to expand off of that in order to create some new techniques, right, in order to help us find volumes and to expand our basic understanding of what it means to be an integral, right? So particularly we're going to start out with this whole idea of the integral as area, or the integral as an area under the curve, and then we're going to work from there in later sections to expand on creating the ideas of volume when we add another dimension, and then eventually we'll work into like different physics ideas that play off the idea of integral as area, but in other conceptual ways. All right, so we're going to start with that. So section 2.1 is going to be about areas between curves. So the integral is basically the area under a curve, right? Between the x-axis, what we've learned is between the x-axis and a particular curve. So we might look at a function. We'll call it f. Here's f. And here's the function f of x, and we've got this interval. We'll call it, in this case, we're going to look at it, we'll make it 0 to a. We don't really care what a is, it doesn't really matter. But what we know is our area is going to equal the integral from 0 to a of f of x dx. All right, so that's fundamental, that this whole area, and we've seen it as like Riemann sums, trapezoids, all sorts of stuff, but this area right in there, that is equal to the integral under the curve f of x dx. Okay. Now let's suppose that we have two curves. All right. So let's imagine that we now have two curves. So we'll have f here. There's f. And then let's say we have a second curve, and that's g. So here's f of x, and here's g of x. And what we want to do is we're going to say, okay, well, what's the area under this curve right here? How big is that curve? That area right in there. So what is that area? A. All right. So what we're going to do is we're going to kind of do something that maybe you did in geometry, or maybe in trig. We're going to kind of think about this conceptually, and what we're going to really think about is we're going to think about like things like negative space, what we call negative space. So what I'm going to do first is I'm going to erase these lines so we can kind of get a sense. Just remember that's the area that we're going to be looking for. And if we first look, the area under f, okay, is going to be this blue area right in here. That's all the area under f, all right? We saw that in the earlier question, okay? And so that area right there, that is the integral of f of x dx, okay? And like again, we're going to say this is from 0 to a. And then let's look at the area for g. So I'll take g and I'm going to make that yellow, okay? And so now here's the area of g, okay? So the area under the curve g, that's g of x dx. Now the area that we want is just the area that's still blue. Remember that? That's just the blue area. So what we want to do is we want to kind of think about this and say, well, what's the most obvious way to think about it, this area, right? We're going to take this big area for f, and we're going to cut out the area for g, and what's going to be left out or left over is going to be the area that we want, okay? So if we think about this, this is going to be 0a f of x dx minus the integral from 0 to a of g of x dx. Now, if you remember, we actually have a theorem that we can use, a subtraction theorem, that will allow us to move this into within the integral. So this is now 0 to a of f of x minus g of x dx. And that's actually how you find the area between those two curves. Is what you're going to do is you're going to take this top curve, okay, and you'll subtract the area of the bottom curve. And that's basically what we're going to be doing no matter what kind of variation we have, is we're going to be taking a top curve, okay, and we'll be subtracting out the area underneath the bottom curve. Boom, there you go. So if we're going to generalize, the generalization is actually going to say, okay, so the area between two curves the integral a to b of f of x minus g of x dx. Okay, where a to b is some interval along the x-axis, or in this case, yep, where a to b, or you could actually make it an open interval if you wanted to too, is an interval on the x-axis. Simple. Now, if you go into your book, you're actually going to see that they've got some different, ways of kind of talking about this. They've got a slightly different theorem, but that's essentially it. That's all. That's what we're trying to do. We'll add in an a here, by the way. That way we know exactly what we're looking for. We're looking for a. So the whole idea here is we're going to take a top curve, f, and we'll subtract from it the bottom curve, g of x, and then we're going to find it on some interval a to b. Oftentimes, the trick for this is actually just to figure out what the interval from a to b actually is. Okay, and we'll talk about that. We'll look at that in terms of some different examples. But let's start out with something basic. So let's find the region bounded by y equals x, or excuse me, y equals e to the x, below by y equals x, and bounded on the sides by x equals 0 and x equals 1. So what we're going to do first is I'm going to first actually draw a graph of this to give me an intuition. And I'll tell you, like, for every single one of these problems, you want to actually draw these graphs. You want to actually give yourself some kind of an intuition, because it's going to make things a lot easier. On your exams, you're also going to have to actually draw a graph. All right, so let's just do that. Get some practice in. You'll practice on each and every one of these. So let me show you what I mean. All right, so we'll start out. We're going to be bounded on the left-hand side by x equals 0. So here's x equals 0. And then we'll be bounded on the right-hand side by x equals 1. So there we go. Now, what that'll mean is that essentially, this is not obviously what y equals x looks like, but let's just use this. That will make that one y equals x, okay, because we'll make this 1. So there's y equals x. And then we'll put up here, here's e. And so consequently, here is e to the x. Y equals e to the x in that region. All right, so on the left-hand side, we've got x equals 0. On the right-hand side, we've got x equals 1. We've got the line y equals x in the bottom, and here's y equals e to the x. And all we're really concerned with is that area in between those two bounds. We're only concerned with this area right in here. So if we think about it, the top curve is y equals e to the x, and the bottom curve is y equals x, and we're going to be looking at it from 0 to 1. Okay, so our interval is from 0 to 1, and one thing that I want to be very careful about, okay, is that in this case, because we're integrating with respect to x, what we want to make sure is that our interval is also with respect to x. That's actually going to become really important, especially in this chapter, where we're going to do more stuff where we're integrating with respect to y, or we're integrating with respect to some physical concept, right? You want to be careful in terms of what are you integrating with respect to. And in this case, we're integrating with respect to 0 to 1, okay? So now the top curve is y equals e to the x, and the bottom curve is y equals x. So utilizing our theory about finding the area between curves, we're simply going to find from 0 to 1 of top curve e to the x minus x dx. And that's actually what we're going to do in integrate. Okay, we'll separate those out. It turns out we can do that in order to make the integration easy. You can't always do this. Sometimes you have to combine. But this time we can. And so this gives me e to the x from 0 to 1 minus x squared over 2 integrated from 0 to 1. And that we'll find is e minus 1 minus 1/2 minus 0. And so this ends up being e minus 3 over 2. And that is the area between those two curves. There you go. If we kind of keep that in mind, this stuff comes out pretty quick. All right. It's about visualization. Can we visualize what the graph is going to look like? And then there's some algebra that's going to go along with that visualization. This entire chapter is going to be about visualization. You want to kind of get really good at that. And if you can, right, then the chapter ends up being a lot easier. And in fact, you get a lot better at calculus and mathematics just in general, and probably engineering or whatever else that you're doing. Now, sometimes we're given the bounds, like we were in the last case. We were given a left-hand bound of x equals 0 and a right-hand bound of x equals 1. Okay, but sometimes we're not. We're actually just asked to find the area between two curves. Okay, so like for example, let's find the area between the parabolas y equals x and y equals 2x minus x squared. And what you'll notice is we're not actually given any bounds there. There's no interval from what to what on the x-axis. So we're actually going to have to go out and find that. So what we're going to do is we're going to first draw the two of these. And y equals x squared, by the way. Let's actually, we're going to draw our graph here. We already know what y equals x squared looks like. So let's actually, in fact, take a look at y equals 2x minus x squared. All right? Because y equals x squared, we can just add in. So y equals 2x minus x squared. What I want to do is I want to put it in some form that I can graph. So that's going to end up being y equals, and we'll make this now negative x squared plus 2x. Okay? And we'll get y equals negative, and this will be x squared minus 2x. Okay? And then we're going to complete the square. So it's going to be negative x squared minus 2x plus 1. And remember with the negative, we're going to have to also make this a plus 1 because this will give us minus 1 and then plus 1. Okay? So y is going to then equal negative x squared minus, excuse me, not x squared, but x minus 1 squared plus 1. So the reason why we wanted to do this, let me put in my bounds here. I've got a 1 here. I'm going to put my 1 right here, okay, is because, right, now that gives me my vertex. My vertex is going to be at 1, 1. And if I plug in 0, so vertex, right, 1, 1, and I have a y-intercept of 0, 0. And there we go. So there is y equals negative x, or 2x minus x squared. Now y equals x squared is just going to look like that, right? There's your y equals x squared parabola. Okay. So what we're going to be looking for is we're going to be looking for the region bounded by these two curves. Okay. Now, upon inspection, the x values for the intersection of these two curves is, in fact, is 0 to 1, or 0, 0, and 1, 1. So those are the intersections, and their x values now are going to be from 0 to 1. There's my interval. Okay, you can see we're going to go from here to here, right, where the two actually intersect so that we can then find the area between the two curves. That's the notion. That's the idea. Now, what if, for example, we didn't actually, it wasn't obvious, right? It's clearly obvious in this case where they intersect. Well, if it wasn't obvious, then what we can do is we could actually set the two functions equal to each other. We could find their intersection, right? Okay, we could find an intersection, all right, by taking x squared equal to 2x minus x squared, okay? And this would then give me 2x squared minus 2x equals 0, just by moving everything over. And then I would end up with 2x times x minus 1 equals 0. And so then x would equal 0 and x would equal 1 would be my points of intersection. That's where that statement would be true. And then that would give me my interval. So that's a secondary way that we can go about actually finding the intersection between the two curves, is we basically just set the two curves equal to each other, okay? And we go solve for, in this case, x. We're going to see another example where we're going to solve for y. So just be careful, you know, what are you integrating with respect to? In this case, since we're integrating with respect to x, we're actually going to be finding the interval for x. We're going to set the two functions, the two y's equal to each other, right? And so we're going to be looking for x's, right? These x's right there. Okay, so now we've got our picture and we've got our bounds, and that actually makes life easier for us, because now all we've got to do is we basically got to go out and we've got to find the value for the integral, right? We've got to write out our integral. So my top function is 2x minus x squared, and my bottom function is y equals x squared. So what that means is that I'm going to have that my area between the two curves is going to be the integral on my bound 0 to 1, because that's what this bound is, of my top curve, 2x minus x squared, minus x squared, okay, dx. And so all of that combined. Now, notice that I actually put them all in brackets, and that's just an algebraic thing to make sure that we end up with the right signs. You can have far more complex functions, and if you've got that, you got to make sure that your bounds are properly placed. So we now have 0 to 1. Or not, excuse me, you got to make sure that your signs are correct. That's what I meant to say. So we now have 2x minus 2x squared dx, and that'll end up being 0 to 1 of 2x dx minus the integral from 0 to 1 of 2x squared dx. So notice this one actually we went in and combined. So this is now x squared from 0 to 1 using the power rule, minus 2/3 x cubed from 0 to 1. And if we solve, we end up with 1 minus 0 minus 2/3 minus 0, which ends up equaling 1/3. And that is the area between those two curves, is 1/3. All right? Once again, if we kind of look at this, there's a process. All right? And we're going to look at that process. I'm going to actually enumerate that process right now. So what is the process? 1. Okay? We're first going to draw the two curves. This is going to help us in terms of every step along the way. So we'll draw the two curves. Okay. Then 2, we're going to find our bounds, either by inspection, if we can do it that way, or by setting the two curves equal to each other. Or we have the other one, which is where we're given given the bounds. Okay, 3. Then we're going to find the integral of the top curve minus the bottom curve on the bounds. Now, sometimes what's going to happen is we're going to get something a little bit more tricky. And the thing is that if we think conceptually, it's a lot easier to do this kind of work versus like I've got to figure out all the different ways that I could possibly see these particular kinds of problems. So probably the best thing for us to do is to go in here and say, okay, well, given that that's the case, what's the top curve, what's the bottom curve, and on what bounds? All right. So like let's take an example. We'll take this example number 3 so you can see what might happen. Okay, so we want to find the area between the region bounded by the curves y equals sine x, y equals cosine x equals 0, and x equals pi over 2. And you're thinking to yourself, oh, awesome. So I don't have to actually go out and figure any bounds. Well, let's draw a picture of this because like that's the first thing that we do in order to give us some intuition. So we'll start out with y equals cosine x, right? So here's pi over 2. Here's 0. We got cosine x. There's cosine x. Boop. There you go. Cosine x. Awesome. On the bounds, that's good. So it's cosine. And let's look at sine x. Well, here's sine x, right? There's sine x. Not the perfectest curve, but that's okay. Y equals sine x. There we go. There we are. And so we want to know the area between the two curves. And you're like, okay, all right, well, what does that mean? Well, just look at it. It's this. That's the area between the two curves. But then also from 0 to pi over 2, that's also the area between those two curves. Okay. Well, here's a problem. Which one's top and which one's bottom? Well, the problem that what we're going to do in order to solve that problem is we're actually going to say, well, on a part of the interval, cosine x is on the top. And on another part of the interval, sine x is on the top. Okay? So what we're going to have is we're going to have two areas. We'll call one area 1. And that integral, it's going to be on some interval. We'll call it a to b right now. Okay? And that's going to have cosine x on top minus sine x dx. And then we have a second area, area 2. All right? And here's area 2. Okay? There's area 2. And area 2 is going to go from b to c. Well, actually, it's going to go from b to pi over 2 if we look at it. Okay? And that'll go from sine x minus cosine x dx, because now sine x is the one on top. By the way, this first one actually doesn't go from a to b. It's going to go from 0 to b. So 0 to b of cosine x minus sine x, and the area 2 is going to go from b to pi over 2 of sine x minus cosine x. All right? Because we switch which one is the top and which one's the bottom. All right, well, if that's the case, right, what's this point? That point right there is b. And you probably already know what the point is. That point is where sine x, so b, is where sine x equals cosine x. And hopefully I don't have to tell you that that's when x is equal to pi over 4. It even looks like it, but you should know that sine of pi over 4 equals cosine of pi over 4 on 0 to pi over 2, right? If not, you want to go back and study some of your trig. All right, cool. So what we're going to do is we're going to treat them as two separate areas, okay? So our overall area, big A, right, is going to equal a1, a sub 1 plus a sub 2, which is going to equal the integral from 0 to pi over 4 of cosine x minus sine x dx plus the integral from pi over 4 to pi over 2 of sine x minus cosine x dx. So what we'll do is we'll just actually separate them out into two different areas. Boom. Okay. And we'll find the area of each individual section, right? Just depending upon which one actually ends up being on top and which one's going to be on bottom. Trick here is really to be able to visualize the two and to be able to find what B is, like where do they actually switch from bottom to top. Okay, and that's it, right? Same principle, okay, just a different kind of visualization. I'll leave the integration to you. It's not terrible integration. You can probably do it on your own. Well, hopefully you can do it on your own. So we're going to look at one more example. And then this next example, what we're going to do is we're going to say, okay, well, let's actually integrate with respect to y. And that might be a foreign concept to you. You might not have actually done any integration with respect to y. You might even know what I mean by integrating with respect to y. So what it means to integrate with respect to y is it means that instead of the x-axis being like your bottom, right, or being the bounds for which you're integrating, it's going to be the y-axis. And sometimes we want to utilize the y-axis, or we want to integrate with respect to y, because it's a lot easier to work with the functions with respect to y. All right, it's a lot easier to do that integration. The integration with respect to x might be very hairy. It might be very problematic to be able to do that. Okay, and so instead what we want to do is we want to think, okay, well, what if instead I look at the area under the curve with respect to y? Now sometimes it's not even that, right? Sometimes it's just a matter of you're just told integrate with respect to y, right? Or this is what you're going to be integrating with respect to, because we want to find accumulation along this y-axis. Well, in that case, you've got to be able to like integrate with respect to y. So let's take a look at an example of finding these areas between curves, and hopefully what it'll help you to do also is to illuminate what does it mean to integrate with respect to a different variable than x. Integrate in this case with respect to y. Okay, and how do we set that up graphically? Because it's going to end up being really important when we start looking at volumes. So when we start looking at volumes, you're going to be like, oh, okay, now I need to think about it in terms of integrating with respect to y, because we're going to be rotating around y, okay, or around x, or whatever it is that we're rotating with, where we need to think about x as a function of y rather than y as a function of x. All right, so let's take a look at that. So let's take a look at an example. So let's find the area of the region bounded by y equals x minus 1 and y squared equals 2x plus 6. So what we'll get here is, let's first draw a picture of this. Excuse me. Give ourselves an intuition. You might use some graphic technology for things as they get a little bit more difficult. What we're going to get is y squared equals 2x minus 6 is going to have a vertex of -3, 0. Okay, and it'll have a y-intercept of root 6 and negative root 6. Okay, so that's root 6. Okay, and then down here, okay, it's going to have negative root 6. All right, so it kind of look like that. And then in addition to that, here's y equals x minus 1. Excuse me. And so there's our graph. And the region that we're going to be looking for is this region right in here. We're going to be looking for the region between those two curves. Now, if we integrate with respect to x, we're actually going to see we're going to have some problems. So let me actually get out of red, show you what I mean. This one, with respect to x, we actually have two regions. One is going to be this red region right in here. Okay, this region. That one. And then in addition to that, we're going to have this blue region over here. So we're actually going to have two regions. We're going to have to take two integrals. And the reason why we're going to have two regions is because we've got different bottom curves. Our top curve is this curve right here. Okay, let me get a highlighter out, show you. Here's our top curve, right there. And then this, for the red region, there's the bottom curve. But for the blue region, the bottom curve is y equals x minus 1. All right, so we actually, what we're going to end up having to do here is we're going to end up having to take two integrals if we do them with respect to x, right? The first integral is going to be the top curve will actually be y equals the square root of 2x plus 6, positive, because that's the top half of this parabola. And then its bottom curve is going to end up being y equals negative root 2x plus 6, because that's actually this bottom curve right there. It's the same parabola, but if we write it as a function of x, we're going to have to account for the negative and the positive side. And it turns out that y is not a function of x, right? It doesn't pass the vertical line test. So we've got to kind of break it up. We've got to turn it into two separate functions. Then, so that's for the red part. For the blue part, it's going to end up being our top will once again be y equals root 2x plus 6, okay? And then we'll also have our bottom is going to end up being now y equals x minus 1. So that's the bottom curve, all right? In addition to having kind of like be somewhat tricky in terms of visualizing what it is in terms of our curves, what we're going to see too is that, all right, here's for this top curve, we'll call this is 3. It's going to go from 3 to whatever this value is right here, okay? Whatever that value is, because that's the end of the parabola. So we'll call that 3 to a. So we'll have to figure out what that intersection is here in terms of x values. And then our second curve is going to go from a, right, to call this b, right? That's going to be the very end point in terms of x values, right? So there's the second x interval. So truth be told, that's kind of complicated, all right? But if we can switch our thinking, okay, if we can switch our thinking, we can actually see this being a little bit different, all right, or being a lot easier to do. And what we're going to be doing is we're going to be writing this as x is a function of y and integrating with respect to y. So now, instead, let's look at this and we'll say, okay, well, instead of looking at it in terms of all right, in terms of integrating with respect to x, we're going to do it with respect to y, and what you'll see is you have a furthest most left curve, okay, which is our yellow curve right here, right? And if you think about that, that's kind of a bottom curve. We'll talk about that in a second. And then we have a furthest most right curve consistently, and that's y equals x minus 1, okay? And that's the furthest most right curve. So if you kind of imagine, what you'll do is you can kind of turn the axis to where the x becomes the y-axis and the y becomes the x-axis. And if you do that, if you kind of like do that in your mind's eye, what you'll see is very clearly the top curve is that blue curve, y equals x minus 1, and the bottom curve is y squared equals 2x plus 6. Nice. That's great, right? Because then you're just like, oh, I'm just going to subtract those two. Cool. That's the concept. Right? And the concept is like, oh, now I only have to integrate once instead of having to integrate twice and finding two sets of bounds. Great. That's really good news. For us to do that, though, what we're going to have to do here is we're going to have to just be able to visualize a little bit differently and find some different values. So one, we have to get that instead of thinking about the interval with respect to x, it's going to be with respect to the y-axis. So they're going to be these y values for our interval. And if you see here, the bottommost y value is this one here. We called it before, we called it a. We called it a, and the topmost y value here is b. Okay, so we're going to have to figure out what a to b is, but those are just the intersection of those two curves in terms of y. That's it. The intersection of those two curves in terms of y, we're going to find that. And then in addition to that, well, how do I write the top curve? How do I write the bottom curve? Or how do I find the furthest most right curve minus the left curve? Okay. Well, again, we're just going to write these two curves as functions of x. All right. So let me show you what I mean by that. So we've got y equals x minus 1, and we have y squared equals 2x plus 6. Okay. Now, this one here, that's our right curve, and this one here is our left curve. All right, and if we remember how we visualize it, this one's going to be kind of our this one is going to be y equals, this one will be our top curve, right? It's got the biggest y values, or excuse me, the biggest x values. And this one here, my left, is going to be my bottom. All right, so we're now going to switch them around. We're going to write x is a function of y. And so that means that this curve right here, the first curve, the right curve, is going to be y plus 1 equals x. And the left curve is going to end up being, we'll do just a little bit of algebra. We end up with y squared minus 6 equals 2x. And then we'll get 1/2 y squared minus 3 is equal to x. And that's all we need to do. All right. Now we need to find the intersection of the two of them. Well, we have them in terms of x. So we're going to set them equal to each other once again, just like we did before. But now we're going to do it with respect to y. So y plus 1 is going to end up equaling now 1/2 y squared minus 3. I'm going to multiply through everything by 2. All right, just to make my algebra a little bit easier. So this is going to be 2y plus 2 equals y squared minus 6. Move everything over to one side. I end up with y squared minus 2y minus 8 equals 0. So this is going to be then y minus 4 times y plus 2 equals 0. And so then y equals -2 and 4. And that's my interval, right? That's that value on the graph. That's this, the y value here, okay? It's something -2, and the y value up here is something 4. And I don't really care what it is, all right? All I need to know is what that y value is. I don't need to know what the x value is, okay? So now I'm going to put those in, and I'm going to do now my area is going to equal right minus left instead of top minus bottom. Okay, so I'm going to do that. It's going to end up equaling the integral from -2 to 4, okay, of y plus 1 minus 1/2 y squared minus 3 dx. And I will let you guys integrate that. That's just some power work, okay? So what you want to get here is that this is a shift. It's a shift in how we visualize the graph and visualize the curves and the areas between those curves. If we're going to integrate with respect to y, remember that you're going to be looking for your intervals with respect that are going to be y values, right? The bottommost y value minus the topmost y value, okay? And we're going to be subtracting right minus left. So the furthest most right curve minus the furthest most left curve. And I know we're probably mirrored on video. You can kind of get when you're looking at your graph, that's what you're going to be doing. Right minus left, okay, and utilizing the interval along y. So that's how we work with the area between curves. Essentially, this big idea, okay, is the area is always the integral under the curve, right, along some kind of interval. And so in order for us to get more complicated, do more complex work, all right, what we're going to start out with is this idea that if I want to find the area between two curves, I just subtract them. I find their points of intersection, and then I subtract the top minus the bottom. Or if I'm doing it now with respect to y, I'm going to subtract the right minus the left. All right, so this completes the lesson.